So without further ado, I'm going to introduce this year's first student presenters, the undergraduate team from Penn State University, Justin and Kevin.
Hi, everyone. Hello. As new technologies emerge, they must become more functional and more available to society to reach their full potential. The desire to make 3D printing more functional is what led Justin and I to develop EchoDrive, what we hope will be the next dimension of 3D printing. EchoDrive is an add-on for 3D printers that makes them automated. It lets them print multiple things out in succession without ever needing anyone to return to the machine. Now, I'm sure many of you in Vent teams are very familiar with 3D printing. We have Dr. Seema here to thank for that. We all know what an excellent technology it is. But there's still one problem with traditional printing. You can't make more than one object without having to return to your device to remove that object and then start the next one. So you can't print multiple things out overnight or a weekend when you're away from your school. And it was this problem that we set out to solve. So Justin and I are 20. We're not far removed from you guys, so we want this talk to be more than a sales pitch. We want it to be about the lessons we learned going through this process and things that you guys probably can identify with as well. So the first thing that we have in this process is having a team. And this is by far the most important part of the invention process in our idea. So I'm Kevin Paroda. I'm a biomedical engineer, just finished my second year.
And I'm Justin Keenan. I'm an electrical engineer and physics major. And on top of having a great team, you need to have a mentor. And let's give a round of applause to all of our mentors here. Teachers and everything. Our mentor, Dr. Sven Buin, actually really pushed us to, invent and design our products. And through several iterations of our designs, we were able to figure out things that we over-designed and made really cumbersome. And also were able to push us in sort of this add-on for 3D printers that we have today.
So to describe our invention, we're actually going to do it in sight of the 4 steps that we see in our own invention process. Idea creation, proof of concept, designing for functionality, and execution. So we'll start with the beginning, idea creation. And for Justin and I, once you figure out the problem that you're trying to solve, idea creation is, of course, the next logical step. And it's one that a team is very important for us. So Justin and I sought out to solve this problem in the simplest way possible. And we did this by challenging each other with these 4 questions. So what do we need to do? Why is doing this a problem? What's a solution to this? And then why is that solution a problem? And so Justin and I go back and forth and challenge each other's ideas and try to figure this out. So for us, we need to remove finished parts from printers. Why is this a problem? Well, in 3D printers, when you make a part, that sticks to the surface of the printer, the build plate. This means, of course, that you have to remove it. But removing that surface is difficult because, again, it's stuck to that surface. So our first idea was, what if we don't remove it from the surface it's stuck to? What if we remove the printer or the surface with the part stuck to it from the printer? Now, of course, there's still another problem with this. The 3D printers need to build parts on rigid surfaces. And so if you remove the surface from the printer in the means that we came up with, a conveyor, that conveyor is flexible, and so that won't provide a good stable surface for printing. So we go through this iteration again. We need to provide a flat surface for printing, and a conveyor sheet will curl with the printed part. So our next idea was that we hold down the conveyor sheet with a vacuum. This was one of our biggest breakthroughs, and it allowed us to do so much with our technology. When we got to this point, we couldn't come up with any reason why it wouldn't work, so we moved on to the next step, proof of concept. And this is the fun part of inventing. This is where you get to go out and try what you're doing. But as young inventors, we find that this is actually one place where we make the most mistakes, and here's why. We create the super glue prototype. We try to put everything together at one go and make something that works right away, and we run into countless problems that we didn't see because we just couldn't foresee them. And you end up with something with a lot of wires and super glue, and you can't always identify where all your problems are, and you have some serious oversights, like buying a vacuum pump that costs $76 or wheels that cost $20 a piece. Over-engineering can be costly. But beyond that, eventually, once you get through this stage and you work out your bugs, you end up with your first prototype, which is what we have here. And so after a few months, we got to this stage. And once you get there, you can move on to the next step, designing for functionality. How are people going to use your technology well?
So our design is pretty remarkable, and we think that we're able to touch a lot of different people. And once we created a minimum viable product, we were able to take that and design, a whole software suite around it. And so we actually have our, minimum viable product software suite. So it's sort of demo here, where you can log in, has a database link to it. You can actually upload your part with a 3D model renderer, and then, change around some of the settings there as well. And so we got this and we brought it to, people. We got our product out there and we started saying, hey, what do you like about it? What do you not like about it? What actually works? What do you use this for? And that was crucial in, developing what we have. Then we continued to iterate on that design and add more and more features that we saw was necessary.
Yeah. With this, one of the key things that we found is that for an automated printer system, people want to be able to use this from anywhere. So having an automated printer means that it needs to essentially work like a desktop paper printer, an inkjet printer. And so the next step from there is execution. So we've created this technology and we've made it functional for people to use, but then we have to deliver it to people. And your goal with your inventions and your technology, of course, is to make the biggest impact that you can. So we had several things that we had to consider with this. We could, of course, build a new 3D printer that was automated and connected to Wi-Fi and had our software that people used. But many of you already own 3D printers. They're expensive, and while they're going down in cost, many of your printers work very well, although I'm sure a few have problems. But we want to capitalize on this research. And so we designed an add-on for printers. And this let us build a single device that we can fit into over 70% of the printers on the market. Since everybody using this device has a 3D printer, you can print out your own attachments to fit it on. So we build one base unit. It takes about 14 screws to put together, and we give it to people, and then they attach it to their machine. It makes it very easy to get our technology in people's hands. It makes it very functional for them to use. So once you go through this process, eventually you go from your super glue model to something that is much more clean, functional, and works better. So in conclusion, with all of this, what we've created is not just that add-on that makes printing automated. Our system actually makes it so that prints do not warp. The vacuum technology that we developed, we were happy to find that it provided such a stable flat surface for printing that we didn't even need to incorporate a heated bed or worry about what type of material people were using in their printer. Our system works with all of them.
Yeah, such as ABS and nylon and other experimental materials, stainless steel types of PLA infused, and also things like bamboo.
So the lesson that we learned here is that when you push through hard things and things that are more difficult than you find, you end up finding that your solution maybe does things better than you'd ever expect, even beyond that. So in conclusion, we'd like to thank the Lemelson program, Dolly, and all the people who made this possible, our personal mentors back at Penn State, Dr. Beelan, as well as Liz Kissenweather, Mark Gagnon, Lee Erickson, and everybody else who's helped us out, and all of you for coming out here tonight. This was an incredible opportunity for us, and we're so happy to share it with you. So we can take your questions now.
We're just holding the mic until somebody asks a question.
Yeah, we weren't trying to beat anybody to it. Hello. How does somebody get the paper or plastic thing that you actually put the things on as they rotate or conveyor belt?
So the plastic film that you saw in the video?
Yes.
Yeah. So we provide that. It's a very simple material. We can actually tell you it's just PVC. It happens to have great adhesion properties. But that's something that we provide with our system as well, and it's something that we had to consider, again, in the execution phase. How do we make this available to people for the lowest possible cost to the consumer? So it was for us sourcing it ourselves at a bulk and then selling it to the people who have our device.
Mark?
So how do you get the vacuum to actually bond to the PVC plastic?
That's a good question. So the question was, how do you get the vacuum to bond to the PVC plastic? You put the plastic on top of it, and you turn the vacuum on. It's about that simple. Now,
is it a
with
plate
that,
goes over?
our roller system that you saw incorporated into that device, make sure that as that sheet of plastic rolls across our device, it's flat, and thus there are no curls or air bubbles or places where the vacuum doesn't engage with it.
Okay, so your device replaces the usual plate on a 3D printer.
Yes.
Okay.
Yes, you remove the old plate and you install ours in the same way that your old plate was installed.
And we have sensors on there that can actually detect the pressure inside and all of that for a very low cost. So.
Any other questions? Right here.
Yeah.
So what's the actual total cost of the add-on?
Right, so the question was, what's the total cost of the add-on? So I'm glad you asked that. This is one of our favorite parts of our device. Our solution is so simple that we're actually able to provide it for less than 10% what you'd pay for a new printer. So our product will be released on Kickstarter at around $300 when we go there.
And that adds, your whole queuing software as well. So you're able to send prints, through our web-based software for free.
I know right now you use that printer to just advance something that's made on the bed. Do you think in the future that could actually be used to move a model through like maybe the x-axis so you could kind of keep a continuous printing going on the same model, kind of use it like a large extruder?
That's an excellent idea. Yes. That is actually, yeah.
Yeah, so.
Do you want to take it?
Yeah, I'll take this, and this will probably be the last question. And so something that we've actually been developing and sort of one of our next inventions that we have a provisional on is actually a printer that's able to print out objects of unlimited of one dimension length. And you basically can do that by shifting and tweaking a few parameters around with your gantry and the way you slice models, and it's doable. So, yeah.
Thank you.